Thanks, Kate. That was amazing. So I thought I'd just start with a quick bit about me. I am, I guess, professionally qualified as an industrial designer. I have spent a lot of my years designing products for other clients, working in-house and both at consultancies. I came into the plant world from more the food side. So when I was living in Perth, I had a lot of grandparents who would grow their own food in large kind of backyards, and then my parents made the conscious decision to move to apartments when we were quite young. Dad started growing all his lettuce hydroponically in those little PVC tubes. I moved to Melbourne from Perth and found myself in an even smaller apartment that didn't have a north-facing window. So I was like, okay, well, I have to get into artificial lighting. I had a setup much like this. The only problem was when I had mates around, they'd always think I was growing something more nefarious than just like leafy greens and herbs. Being an industrial designer, I was like, oh shit, there must be some kind of better way to do this that can like blend into our living spaces, which kind of started this whole journey into artificial lighting. And I just want to preface all of this. At school, I was hopeless at biology. So all of the stuff I now know I've digested through just pure passion and wanting to know more about it. Kate is kind of being my kind of horticulturalist on hand, which I love because I can kind of combine my knowledge as more of the engineer and knowledge of how to get stuff made with Kate's knowledge of how the plants actually physically grow. So she's been a great help for me along this journey too. So I thought I'd give a brief background on the sun. So the sun kind of is up in the sky emitting photons down to us. If you've ever seen the Dark Side of the Moon album, great album, they've got sunlight basically going into a glass prism and it splits into all these different colors. And that is essentially what we see. However, that is only 42% of what's actually hitting the Earth. So the sun's emitting a lot more wavelengths that we can't see. And so when you go above 700 nanometers, this gets into your like infrared range, and then all the way up to microwaves. And then if you go below 400 nanometers, that's when you get into your UV, your UVA, B and C, kind of the stuff that's quite harmful to us. And fortunately, we've got the ozone layer that kind of filters a lot of that out. Unfortunately, that's kind of getting depleted, but that's another story. I think to understand how plants see light, it's first important to understand how we see light. So our eyes are very good at, I guess, opening and closing according to like how much light is in the room. Our retinas do a great job of opening up and closing, and then that light comes into our retinas and then goes into photoreceptors at the back of our eyes, converts into like electrical signals, and then we kind of interpret that light as objects in front of us. And it's really quite cool how all this happens. Plants, on the other hand, see light somewhat similar but very different. They don't have retinas, so they can't open up and close, I guess, their leaves to let more or less light in. They still have photoreceptors. However, these photoreceptors are quite different, and they are converting that electrical energy into sugars and carbohydrates to basically let it grow. And that's, in a nutshell, very basic photosynthesis. It wasn't until the 1970s that this fella, Keith McCree, came along. He was actually a Kiwi physicist working on streetlights at the time. And he was the first person to kind of say, these are the wavelengths of lights that plants use to photosynthesize. And those are the wavelengths that fall between 400 and 700 nanometers. And that is known as PAR. So whenever you see this on a website, PAR is the photosynthetic active radiation. The problem is that plants are quite sensitive to different wavelengths of our eyes. So we see light, well, we measure light for people in lumens. And our eyes are more sensitive to kind of green light, whereas on the other hand, plants, we measure light in ppfd, and this is I don't want to stuff these up, photosynthetic photon flux density. And this is measured in micromoles per second per meter squared. So it's the amount of photons, the bioavailable photons, hitting a square meter of space every second. And it's quite valuable. I'll go into it later on in a bit more depth and show you the difference between like architecture and horticultural lighting, and you can really see the difference between something that's bright in terms of lumens may not necessarily be bright in terms of ppfd. So I always like to say to people, quite controversially, there's no such thing as a grow light. A grow light is essentially three fundamental things that exist independently, but they're just put together to make sure the plant's receiving adequate amount of lighting. And these things are the quality or the spectrum of light, the intensity or how bright it is, and the duration. And if you have, I guess, any one of these things right independently, you still don't have a grow light. You need to kind of combine all these things together and have the right mix in order for you to have a successful artificial lighting solution. Plants most effectively photosynthesize through two pigments, chlorophyll A and chlorophyll B. And these two pigments absorb light in the 400 to 500 nanometer range, so that's your blue light, and the 600 to 700 nanometer range, and that's your red light. I'll go into a bit further depth later on about why you see a lot of horticultural lightings being blue and red, but first I'm just going to break down the impact of each of these wavelengths. So firstly, blue light, not only being highly efficient at producing at photosynthesis, it also regulates the opening of the stomata on a leaf. So those are the little, I guess, like mouths in a leaf that let in and out oxygen. What's really cool about blue light is that you can actually use it to inhibit stem elongation and leaf expansion. So blue light, plants basically judge light intensity through the abundance of blue light. So if you grew a plant under strictly just blue light, which a lot of like leafy green and herb farmers do, you'll get plants that are tiny because they think they're essentially under just like really extreme intense light, which is like you can start to think, oh cool, we can actually do some really cool things just with light to adjust our plants. For most of us, where we're looking for just like very generic good plant growth, you want about 10% blue light in your overall spectrum in your grow light. Red light, on the other hand, also very good at photosynthesis. However, it reverses the effect of stem, it actually enhances stem elongation and leaf expansion. So blue light and red light are commonly paired together to create a really nice holistic grow light. So farmers will use about 90% red light in their grow spectrums. Then you get on to some more of the lesser used but still kind of important light. So you've got far red light. Far red light exists between 700 and 800 nanometers. It's not quite infrared. You can still kind of see it, but it's barely visible. What's cool about far red light is that it triggers a shade avoidance response. So in a canopy, the top leaves are absorbing all the blue and red light, but what's penetrating below the canopy is actually the far red. So if a plant is receiving far red, it's going to think, oh shit, there's other plants above me, and it's actually going to elongate its stem in order to get to the kind of the upper canopy in order to receive more of that blue and red light that is going to drive more efficient photosynthesis. So there's all these cool like photomorphological responses that plants have according to like the wavelengths of light they're getting. And also they use far red combined with red light in order to regulate germination and flowering. And I'll go more into depth when I get to duration slide of that later. Now, up until recently, a lot of, I guess, horticulturalists, botanists kind of disregarded green light. They said Plants are green basically because they reflect all the green light in the atmosphere. They don't use it at all for photosynthesis. And this is partly correct. So what they were doing was only measuring the top leaves of a lot of plants. What we now know is that a lot of this green light penetrates deeper into the canopy. So you can actually use it as quite an effective color if you've got a very dense plant. You can introduce green light into it, and the lower leaves of that plant will use that green light to photosynthesize. What's also amazing is it can be used as like, if you're walking into a greenhouse at night and you don't want to interrupt the nighttime period, you can use very small amounts of green light, which our eyes are very sensitive to. So the room seems really bright to us, but to the plant, it's still quite dark and still night. So we can go in and inspect our plants under small amounts of green light with great success. Well, there we go. So when I first started this and I told my mates I was making grow lights, they were like, oh, so you're making lights with UV? And I'm like, well, not really. UV is one of those things that plants actually don't need to grow. It can actually be quite harmful to plants if you introduce UV light, and also it's really expensive to produce. So if you're using UV light, there has to be a very important purpose for the use of UV light. A lot of commercial farmers will use UV light, if they're growing organically, use UV light to kill pathogens and bugs and stuff. So at night, they'll flash it with small amounts of like UVA, B or C, and it basically kills life. So it's why you see during COVID, a lot of people use UVA, UVB, UVC lamps as sterilization lamps throughout offices. Then on the other side of the visible spectrum, you've got infrared. This is invisible to us. It's how heat's transferred. So commercial greenhouses, especially in Australia, the biggest problem with us is we're quite a hot climate. So a lot of the time we're looking at, oh no, oh. Sorry. There was bound to be one tech difficulty during this. There always is. Yeah, I know. And I was on such a roll too. Yeah, but I guess while I'm waiting for this to load again, so infrared is the way heat's transferred. We're trying to invent glazings at the moment that eliminate infrared heat transfer. A cool aside, if you buy a Tesla, they've actually invented a biofilm that's located in between the glazing, because a lot of the roofs of Teslas are all like glass, and if you were letting all the infrared heat transfer in, essentially your battery would just get drained in trying to provide the car with cooling. So they're cutting the infrared heat transfer out at the glazing level on a mechanical level, which I thought when I found this out, I was like, oh, that's quite cool. I did a bit of freelancing with a company who was employed by Vic Ag, and they have got a smart farm in Horsham, and we were looking into controlled environment growing facilities and looking at how we could harness this type of glazing in developing, I guess, new ways of new greenhouses. So when we remember back, that's kind of light quality or the spectrum of light. Now we move on to light intensity. I get frustrated when you go to a nursery and you see on the little plant ticket things such as low light, medium light, bright indirect light. They're very kind of vague terms to things that are actually highly quantifiable. I would love it if they started to even just list lumens on there, because that is something that's extremely measurable. You can buy lux meters that measure the sun, and you can say, hey, if I haven't got this amount of light, this is not going to grow. So this is kind of like what I've, over the kind of years of doing this, have said this, the correlation of what to what. So if you've got a quantum quantum flux meter at home that's measuring ppfd, or if you've simply got just a lux meter, I put up there lumens of sun, because if you're measuring the lumens of sun and it's 1800, that's going to be very different to the lumens of an 1800 lumen, just cool white LED. You're not going to be getting the same amount of ppfd. So I always like to say at bare minimum, you want around 40 micromoles per meter square per second. And that is like going to grow most of your low light plants. Anything under that, your plants are going to go into dormancy. And in some cases, they're just going to die. I've been doing a lot of kind of educational pieces with developers and people who are installing green infrastructure. And the thing developers like to do is minimize cost. And having a horticulturalist come in and maintain a green wall is more cost. And if you're, I guess, providing a plant with the adequate amount of light, they're going to actively grow, and a horticulturalist is going to need to come in more often to tend to that green wall. So what a lot of these people do is they underlight the plants, so they're constantly in a state of dormancy, which is really frustrating for me because a lot of these green walls are being installed for like air purification purposes. And if you're wanting your, I guess, air to be purified, you need your plant to be actively growing. So there's kind of this, I guess, educational piece that I'm trying to do with a lot of like architects, builders at the moment. And it is somewhat of a challenge to get people to see the problems of underlighting plants. And I like to say, if your plant isn't giving out new leaf mass, like not like every day, but frequently, it's not actively growing. Like a plant wants to grow, it wants to put out new leaf mass. If it's not doing that, it's pretty dormant. And so this goes pretty much up to most of your ornamentals. Just as like a point of interest, leafy greens and herbs pretty much start here. Anything above that, so you think like a tomato, any fruiting plant needs 800. The sun gives around, on a sunny day, can give up to 2,500 micromoles per meter square per second. So you think the difference between 2,500 and 40, it's quite a bit. And so plants are like your low light plants that have evolved to survive in these conditions are the ones that exist on like your forest floors. And then you've got probably cacti and succulents around this kind of area. I always like to keep most of my plants around 150 ppfd. I find you're not gonna saturate them, or you're not gonna burn them at that level, and they're gonna be kind of healthy and happy. Next thing we come to is light duration, and this is kind of the final piece of the puzzle in creating an effective grow light. There's three types of plants, can be basically grouped into three categories. Your short day or long night plants, which are your plants that flower or grow in winter. Your day neutrals, most tropical plants are day neutral. They really don't care how much light you give them. And then your long day or short night, these are your summer flowering plants. The reason I've kind of put in brackets like long night and short night is because plants actually tell time by the amount of night time they get. So in saying that they're short day or long day plants is kind of incorrect, because they're not judging day length, they're judging night length. A lot of people also think that they do this through temperature fluctuations. However, if plants were to judge day length through temperature, they'd be all over the place because our climate's constantly changing. What's really cool is plants actually have an internal kind of diary. So back when I was talking about near red and far red, in the middle of the day, the quantity of near red is huge. It's like, it's everywhere. Whereas the amount of far red in the atmosphere is considerably less. However, when the sun sets, this starts to change and we start to get a lot more far red existing in our atmosphere than near red. And then during the night, it's only far red. So what plants do is they measure the amount of near red and far red in one day, and then they go, okay, I'm going to measure this for the next 5 days. And they actually keep track of this for an extended period of time. And if they can see that the amount of near red as opposed to far red is increasing, they can say, oh, I must be coming into either autumn or winter. And then they produce the correct response related to that, whether they're a winter flowering plant or a summer flowering plant. What's really cool is we can use this information to basically trigger flowering responses. So if you've got a winter flower that you're looking to, I guess, you're say a person going to market with your flowers and you're wanting to flower in a week's time, you can start to ramp up the amount of near red you're giving the plant during nights, and it will decrease their flowering time. So there's all this cool stuff that you can start to do once you understand a bit more about the spectral effect of lights on plants. However, I think for most of us, we're generally looking at kind of an all-rounder. I think the problem with the internet is that it's got a lot of commercial growers and a lot of commercial cannabis growers on it, especially in like the Reddit spheres. And these people are great because they're like super like interested in producing a certain type of like flavor or THC content. And then that's what becomes really confusing when you're looking at just growing an indoor plant, because you can get kind of muddled up in all this complexity that really doesn't apply to the likes of you and I. And that's kind of where I struggled originally, because I was looking at all these blogs and being like, oh shit, do I have to create a light that's got all these different colors? And it's like, well, no, you only need some of the most important, the red and the blue. And then you can kind of really play around with the spectrum outside of that to make it look more aesthetically pleasing to you and I. And I think that's a good segue into now what traditional lighting solutions have been. So I kind of group them into two categories. You've got your architectural lighting and then your horticultural lighting. The most common architectural light is your tungsten globe. This is the spectral distribution that a tungsten globe gives off. If you remember back to the PAR map, you can see that it's got quite adequate amount of red light. However, it's really lacking kind of the blue end of the spectrum. Not only that, is that these things are really inefficient at converting power, watts, to light. So they're really hot, so a lot of the energy you put into them is coming off as heat. Their luminous efficiency is really low, and their PPF efficiency is even lower. So if you could theoretically use these as grow lights. However, you would need an array probably the size of this roof to even grow like 3 plants, because it's not giving you the amount of light compared to the amount of power you're having to put in to grow these plants. So back when I said every light's a grow light, yes, every light's a grow light, but you're just going to need shitloads of them to be able to grow what you want to grow. Next, you have your kind of your standard cool white LED. And I've said low CRI. So low CRI, it's its ability to reproduce that color as close to daylight as possible. So most architectural lights aren't interested in replicating colors at such a high degree of accuracy. Therefore, they can be a lot cheaper, the actual chips themselves. So here's the spectral distribution of a cool white LED. You notice compared to our tungsten lamp, the luminous efficiency has actually gone a fair bit up. Like, they're really efficient at converting energy to light. We've got a spectral distribution that may be good for like your leafy greens and herbs. However, you're going to get really kind of short plants with not much leaf mass if you're growing under just a blue heavy spectrum. The PPF efficiency quite high, but when going back to what I previously said, it's more about the characteristics of the plant you're wanting to produce. I guess if you're wanting to make plants that are short and small in leaf size, then you could probably grow them under this. You're probably spending a lot more money on energy costs than you would be if you went for like a higher CRI based LED chip. The other end of the spectrum, you've got your warmer low CRI LED lights. Around about the same luminous efficacy, a touch higher because red LEDs are one of the most efficient types of LEDs, so the warmer you get, the better they are. The PPF efficiency around about the same, but again, you're looking at the spectral distribution and you've got quite I guess it's shifted towards the red side, and they're going to seem brighter to you and I because our eyes are more sensitive to those kind of wavelengths of light. And now we get into the horticultural world. So this is traditionally what was used for commercial grade horticulture for many years, high pressure sodium lamps. really efficient, really high PPF efficacy, a spectrum that's pretty good. Most of these lights were used as supplementary lights in greenhouses. So you're already getting kind of the required amount of blue end of the spectrum to make them valuable to a greenhouse. The only problem is they take a while to like heat up and turn on, and also a while to like turn off at night. So they're not as like adaptable as an LED lighting solution. Much the same, you've got metal halide lamps. These spectrums are kind of all over the place. So again, they were used more as like supplementary lighting for commercial greenhouses for a long time. Efficacy is fine, luminous efficacy, I guess we're not, like when you're growing plants, you're not necessarily interested in that, but I thought it'd be just interesting to show the comparisons of different types of lighting solutions. And I guess this is kind of where we are today. LED lights in comparison to lights in general are still fairly new on the scene. We started using blue and red lights because they were the most efficient at producing the photons of light that plants needed to photosynthesize. Red lights are efficient at turning power into photons. Blue lights were some of the cheapest LED lights to make. So a lot of commercial farmers went, okay, we're just going to use these two LEDs because they're cheap to run, cheap to make, very like low CapEx and OpEx costs. And when you're a commercial farmer, every single cent you put into what you're doing equals the cost of goods and what you can go to market with. Where we are today is actually really cool. So we're producing a lot more broad spectrum LED lighting solutions. This has only really been possible with the mass adoption of white LEDs as a viable lighting solution for architecture. So when people started to use these in general, the cost came down, which made them more available to the general consumer. And so stuff like this fixtures like this Mars Hydro quantum board now combine 3000 Kelvin and 5000 Kelvin LEDs with a high color rendering index, and that's because the 5000 Kelvin LEDs provide them with that blue peak, and the 3000 Kelvins provide them with that red peak. And then they boost the efficiency with just a few red LEDs. So when you see a board like this, the reason you'll see these red LEDs is basically to get that PPF efficacy up. It's not necessarily needed. You can grow plants under a quantum board without these LEDs. However, for, I guess, again, commercial grade farmers, they all care about how many micromoles per watt that light source is producing, because then that is their cost of end goods. So for us, you could literally grow your plants underneath a 3000 Kelvin LED and it's going to be fine. I would say if you're wanting just a single diode solution, you may be wanting to go towards 3500 Kelvin. I'm doing a couple of tests in my studio at the moment where I've got a 3000, 3500, 4000 and 5000 Kelvin LED strips. And I'm wanting to really see if at all there is much difference in plant growth based along those spectrums. There's been like kind of, all the research has come from the agricultural side or the cannabis side, and it's really frustrating because it's like they're always interested in efficiency, and I'm like, yeah, but I'm interested in light that looks good to us as well. So it's kind of a bit of a balancing act, which I guess brings to my product. I designed this about a year ago, looking at creating a custom chip. So I've essentially designed my own quantum board and put it in a circular solution. At the time, there wasn't really any commercial manufacturer making chips in the form factors that are used for decorative lighting pieces. So you could buy the big kind of, the larger quantum boards that you see, but there weren't anybody making them in, I guess, modules that I could then use in nicer lighting pieces. So I said, okay, well, with my knowledge of what chips I need to go onto the board, I can create my own modules. Then I put a control board into the base where you can adjust the power and the brightness according to the plant type, along with the photo period or the duration it's on. And also tried to make it look nice, which Kate keeps reminding me that I do a good job at. So yeah, I think that, to summarize, I think I want to stress that the fact that grow lights don't need to be complicated. If you're looking to buy a grow light, as long as you go, okay, I've got around 3,500 Kelvin spectrum, a high color rendering index, and the correct amount of like power, it's going to be a successful grow light. Like Callum grows his plants with a floodlight in the middle of his lounge room, and it works fine. Yeah, and I think there's a lot of information out there that wants to make this space really complex. However, it doesn't need to be. There are, again, on the flip side, there's a lot of options that claim to be to promise the world. I would steer away from the blue and red spectrum. They don't look nice. They may be efficient, but I did the sums on running this for 24 hours a day for 365 days a year, which is like a lot longer than you'd ever run it, and the most it's going to cost you is around $35. So per year. So it's like you may save yourself 10 cents a year by switching to a narrow band spectrum, which really isn't worth it for the aesthetic value of having a disco light in your lounge room. Unless you want that, by all means, if that's your aesthetic, then go for it. So yeah, I'm Charles. I essentially, at the moment, sole founder of Ample. If you've got any questions, I love talking about this subject, as you can tell, so you can hit me up via my email. My Instagram's @growample. We're due to start assembly for our first product, PL1, earlier next month. We're currently running a pre-order on our website. So jump on there if this is something that interests you. Otherwise, if you've got any questions at all, feel free to hit me up. If you're looking at a grow light and just want to know if it's something that's going to work, I'm more than happy to have a bit of a yarn about it. And yeah, hopefully did some help today in demystifying plants and light. Cool. Oh, I forgot to mention, if you've also got some questions now too, I'm happy to answer them.
Dual channel architectural lighting?
Yes.
How do you think that stacks up? Because I know a lot of things like, say, Philips has a line.
Yep.
IKEA, I think, also does.
Yeah.
It's a dual channel system
Yeah.
that allows you to move across
Yeah.
the spectrum.
For sure.
How do you think that stacks up compared to, say, like a single channel
Yep.
architectural light?
Yeah. So the way a dual channel light works, it will have the same amount of diodes that you see on this board. However, it will separate them into essentially two channels. So if you're adjusting one channel, it will dim the other or turn the other channel off. So they'll say we're dual channel 2700 to 6000 Kelvin LED. What that means, it's got a certain amount of 2700 Kelvin LEDs on there, and then it's got a certain amount of 6000. And it's just adjusting the brightness. So you'll never have them, if you're wanting the peak intensity either end. So dual channels are great if you're wanting to shift your spectrum. You're just going to be forfeiting the power, the brightness.
So you want to go dead center then?
Yeah, and I want to get into cool spaces where I'm making dual channel LEDs, but using it for the spectral changes of a sunrise and sunset. Yep. So not necessarily doing it for tuning purposes, more doing it for the aesthetic. Yeah, and you're using all of those LEDs at full brightness at the peak of the day, but at the start and end, you're kind of dimming them to I guess, make that color change as close to the sun and sunrise and sunset as possible. Yeah. And
thank you very much.
Sorry, I got a question down the back.
Kimberly. So, can't afford something as stunning as that for each individual
Yeah.
bundle. Things like the T8 Barona or like the T5 Barona that we see as broad spectrum grow lights, how do we determine how good they are and whether they're really giving us what our plant needs rather than just looking gorgeous and bright and
Yeah. So, oh no, it's not in my back pocket. There's a couple of ways. I have got this nifty thing called a quantum flux meter. So that basically, like, you can get lux meters, which measure the brightness for you and I, but this measures the brightness for plants. And if you go around and just put it in front of the light and be like, okay, I'm getting this much. And also you want to see how uniform that light spread is. Because obviously when it's like dead in front, it's going to be a hot spot, but then lights can really drop off if they've got no lensing options towards the edges. So you may need to like do some nifty things where you're like arraying these to like make sure you've got even distribution all around your plants. I recently downloaded an app called Photone. It is quite a good quantum flux meter for just in the ranges of 40 to like 100, 150 ppfd, which is really the kind of area that we're interested in. Lower light levels, it doesn't seem to be so accurate. Higher light levels, again, doesn't seem to be accurate. There's a pro version where you can adjust what spectrum you're growing under. So when you buy the light, it'll more often than not list what color temperature it is. And then you can calibrate that app. This does it automatically. The app, you kind of need to tell what light you're growing under, be it full sun, cool. These look like more of a cool LED, or your warm LED, or your broad spectrum, or your narrow band. There's heaps of options. Like, I think the Pro version's even got like high pressure sodiums and tungsten lamps in the app, and it tells you basically the ppfd output of that light. So that's a great way. And if you have those things, you can quite easily just go in and troubleshoot all your plants. Again, going back to that slide with light intensity, you kind of wanted minimum requirements 40 and above. If you're wanting active growth, I'd say keep it above 100, 150. And yeah, you really can't go wrong if you're hitting those benchmarks. There's no reason to say why your plants won't be successful. It all comes down to like, if it's a cool spectrum, you're gonna maybe have some differences in plant size, but for what we're doing, I don't think it's gonna be super noticeable. Maybe if you grow it in like a really red dominant spectrum where it's almost like just red light, you're gonna notice really elongated, leggy plants. But most of us aren't going to be converting our entire house into a red light district anytime soon.
Does dimming increase efficacy or reduce efficacy?
Reduce. So all dimming's doing is kind of changing the brightness. Yes, it does do some things on an electronics level where if you're running, so there's various ways to dim without going into like circuit board architecture. The most common way of dimming is through PWM, and that's through a constant voltage system where you're adjusting the ampage. So running your lights at a lower ampage is going to make the LEDs themselves more efficient because the cooler they are, the better they are at converting energy into photons of light. Yes, so a lot of chip manufacturers will list the efficiency or efficacy at a certain current rating. So more often than not, it's 650 milliamps. They'll say, this is where we're gonna say it's most efficient. Yeah. However, like I know the chips I'm using, the Samsung LM301Hs, they say they list it at 650 milliamps. However, you can drive them all the way up to 200 milliamps. So the PPF efficacy is going to drop off slightly. So I think at 650 milliamps, it's I think 200 milliamps, it's around 2.5, and then at 65 milliamps, it's around 3.
So your energy consumption increases at efficiency of light?
Yeah, the efficiency of light. So it's drawing more current from the supply in order to increase the brightness. And then you can get things like when it starts to heat up, you can get thermal runaway, but that's like a electronics thing, and you can minimize that through different resistors and all of this. But yeah, I mean, I could go into another talk completely on just like electronics and board design and all of that, but I think it's way above the kind of level where we need to know. Fortunately, I know that, you don't need to know that.
All right, thank you so much, Charles. If anyone has any other questions, Charles will be hanging around. So you can come and ask Charles face to face or via Insta.
Yeah, DMs.
Feel free to hit him up. So thank you very much. I actually learned how to get there. That was awesome.